In last class, we discussed time dependence of expectation values. We have taken one operator B that need not commute with A or H. H is Hamiltonian operator. And we have taken this operator at time t equal to 0. We found the expectation value and we got A dash B A dash. And at later time t, again we found the expectation value of this operator and we found that that is equal to expectation value of B at time t equal to 0. That means for a single state, the expectation values will not change with respect to time. So we called it as stationary state. Then we discussed a non-stationary state. A non-stationary state, that means the state is the superposition of two or more different energy states. And we found that at time t equal to 0, we got one expectation value for this operator B. And at later time t, we got another expectation value that is different from the expectation value at time t equal to 0. That difference was e raised to minus I Ea double dash minus Ea dash t over h cross. That means this expectation value of this operator is oscillating with respect to time, is changing with respect to time. That means it is oscillating with respect to time with a frequency of omega, angular frequency of omega, a dash a double dash equal to e a double dash minus e a dash over h cross. With this frequency, this expectation value at a time t is changing. Okay. And this way, this is actually mathematical steps we have been done, different mathematical steps we have been done. We need to take a physical example to examine whether this mathematical example was correct or not. Or let me show by taking a physical example to explain this mathematical steps well. Okay, so actually we have developed our fundamental concept by starting with the Stern-Gerlach experiment, a spin half system, and through that spin half system we have taken a Stern-Gerlach experiment. Through that Stern-Gerlach experiment we have discussed, we have developed our complete fundamental concept of the quantum mechanics. Okay, let me take that example itself. That example itself to prove this mathematical steps were correct. Okay, so we are going to another topic. There is an example, there is spin precession. I hope this is visible to you. And here we are taking a spin half system with a magnetic moment EH cross over to MEC. Okay, that spin half system is being subjected to a magnetic field that is B. So I hope you remember our Stern-Gerlach experiment. One silver atom, its orientation, spin orientation actually we don't know. That spin orientation we don't know, and this silver atom is being subjected to a magnetic field and it's moving towards one direction and it makes two spots in a screen. And we got angular momentum, the magnitude of angular momentum as h cross over 2, and the direction of that angular momentum we got plus z direction and minus z direction. Okay, this experiment or this concept we have been developed in last chapter, and that we are going to take as an example. So the interaction energy, when this particle is moving through this magnetic field, it will get an energy, it will have an energy, interaction energy. That interaction energy is that is equal to interaction energy we have taken U equal to minus mu dot B, or you have learned as interaction energy is minus m dot B or mb cos theta. Here we are taking minus mu dot B, minus mu dot B. as an interaction energy. That interaction is the total energy of the system. That total energy we are taking here as Hamiltonian operator, that is equal to minus mu dot B. That is equal to minus E over MEC plus or minus H cross over 2. Here we are taking a magnetic moment EH cross over 2 MEC, and that we will get like this: E minus E over MEC plus or minus H cross over 2 in some direction, Z direction, dot B. Okay, this is our spin term SZ, or S. This is our spin term S dot P. We can write as S dot P. This plus or minus H cross over 2, we will get whether it's going upward or it will go downward. So that is equal to minus E over MEC S dot B. And let us consider this magnetic field B as constant. A constant or uniform magnetic field is there. We are applying a uniform magnetic field, and when we are applying a uniform magnetic field, spin should be either is in positive Z direction or is in minus Z direction. So we can take the spin as SZ, and this P is constant in Z direction. Okay, this both are in same direction, so this S dot B we can take as SB, SZB. Okay, so that is Hamiltonian H equal to minus EB over MEC SZ. This value of this E, when we are considering as an electron, E is less than 0, so we will get Hamiltonian as H equal to EB over MEC into SZ. Okay, and the difference between this spin SZ and our Hamiltonian H is just a multiplicative constant minus EB over MEC. Okay, that means this operators should commute. That is equal to minus EB over MEC SZ equal to 0. This should commute means when we are considering commutator of two operator, AB equal to AB minus BA. That is, this is a similar operators, so AB minus BA we will get equal to 0. That means SZ and H commutes. If two operators are commutes, then their energy, their eigenstates are similar. Okay, the eigenstate of one should be the eigenstate of the other operator too. Okay, so this eigenstate of H is eigenstate of SZ2. So the corresponding energy eigenvalues will find if you are operating H on plus SZ plus state, that is equal to minus EB over MEC SZ. This is our H SZ operating on plus state, and that is equal to minus EB over MEC H cross over 2 state SZ plus. Okay, so we will get energy eigenvalue as minus EB H cross over ME C2 for SZ state, and for SZ minus state, here we will get a minus sign. Okay, when we are taking minus SZ minus and we are operating with the Hamiltonian operator, we will get E minus equal to minus EB over MEC into minus H cross over 2, that is equal to EB over MEC H cross over 2 for SZ minus state. And then we are taking the difference, that is E equal to E minus minus E plus, that is equal to EB over MEC H cross divided by 2 minus minus EB H cross over MEC 2. Okay, that is equal to EBH over MEC. So H we can rewrite as omega Z, and the time evolution operator is in the form given here. Let's expand state alpha, that is equal to expansion coefficient C plus SZ plus state plus C minus SZ minus state. Okay. So at later time t, we can expand this as alpha at later time t, that is equal to C plus e raised to minus I omega SZ t over h cross plus c minus e raised to minus I omega sz t over h cross minus. Okay, this way of expansion we have learned earlier, so just apply here, and that is equal to c plus this we can expand as 1 minus I omega t over h cross sz plus this etc, like e raised to x we are expanding, and operating on plus state plus c minus and we will expand again 1 minus 1 plus x square, like that is operating over minus sz minus state. That is equal to, we can take plus state minus I omega t over h cross sz is operating on plus state. If sz is operating on plus z state, you will get an eigenvalue h cross over 2 plus, okay, plus like that. If this operates on twice, operate this value on twice, we will get h cross square over 4, like that. So, and here also it's like that. Here we will get an eigenvalue minus h cross over 2 and minus h cross over 2 whole square. Okay, this h cross and h cross will get cancelled. This h cross square will get cancelled, and we can again write it as c plus e raised to minus I omega t over 2. This is the eigenvalue plus state plus c minus e raised to, this is the eigenvalue e raised to plus I omega t over 2 and minus state, where we have used h plus or minus equal to plus or minus h cross omega over 2 plus or minus. Okay, let us take this initial state. Initial state itself, alpha represents a spin-up state. That means in our Stern-Gerlach experiment, it's North Pole, South Pole, we are sending an atom with SZ direction. Okay, we are sending an atom, silver atom, that oriented in SZ, already oriented in SZ direction. Surely we know this will go in upward direction. Okay, this will go in upward direction on this screen. Okay, we know this will not go downward direction. This will take only plus h cross over 2. Okay, that means c plus equal to 1 and c minus equal to 0. Actually, our state we used to expand as c plus c minus minus. Okay, so if we are, the initial state itself is a plus state, then this c minus equal to 0, that I have mentioned here. Okay, that is c plus equal to 1, c minus equal to 0. And at later time, alpha t equal to 0, t at later time, look at here, this is c minus. So at later time also, this c minus we have already taken 0. So at later time also, this is equal to c plus e raised to minus I omega t over 2 on our plus state. That means at time t equal to 0, alpha equal to c plus state. That means this is the expansion coefficient and the state is this one. Okay, and later time also, this is the expansion coefficient and state is this one. Okay, that means that state will not change with respect to time, and this is known as stationary state. Okay, in time dependence of expectation values also, we have taken a single state and we found that at later time that state will not change or state will not change with respect to time, and that's why it was known as stationary state. And here also at later time, for a single state, that means alpha is a single state, not a superposition of these two states. We are taking it as single state. This equal to c is equal to 0. We are taking it as single state, and the state will not change with respect to time. Okay, and now we are going to take we are going to take a state that's a superposition of some other states. Okay, for an example, here we are taking an Sx plus state, which is a superposition of Sz plus state and Sz minus state. We have learned it earlier. So the expansion coefficients are C plus equal to 1 by root 2, C minus equal to 1 by root 2. Okay. And we will verify the probabilities of system to be found in Sx plus state at later time t. Okay. So at later time t, we need to find out the probability of finding this particle in Sx plus state. Okay, so we are finding the probability. Probability is mod the square of the mod of the inner product of Sx plus and alpha at time t. So this is the way which we are finding the probability at later time t. Probability of finding the particle Sx plus at later time t. Okay, that is equal to Sx plus is initially Sx plus 1 by root 2 plus 1 by root 2 this bra minus into 1 by root 2 at later time alpha. We have expanded as 1 by root 2 e raised to minus I omega t over 2 plus 1 by root 2 e raised to plus I omega t over 2 minus mod square. That is equal to first we have to multiply this with this one. We will get 1 by 2 e raised to minus I omega t over 2. Then we have to multiply this with the second term, but we will get 0 because here is the state plus and here is the state minus. Okay, so inner product of plus and minus will be equal to 0. So we need not multiply that with this one, and then we take the second term and we will multiply with this one. Okay, then again we will get 1 by 2 e raised to I omega t over 2 whole square. That is equal to 1 by 2 e raised to I omega t plus e raised to minus I omega t whole square. That is equal to this term is 2 cos omega t by 2. Okay, because e raised to theta plus e raised to minus theta over 2 e raised to I theta plus e raised to minus I theta over 2 equal to cos theta. Okay, using this identity we have reached in this step, that is equal to 1 by 2 cos omega t over 2 whole square. That is equal to cos square omega t over 2. Similarly, if you are finding the probability of Sx minus state, okay, finding the probability of finding the particle to be in Sx minus state at later time t is, we used to find in this way itself. That is, we are putting Sx minus here and we are finding the probability, and we will get, that is equal to, I am not doing here because this is one example I have done. So through these steps, by looking these steps, you can find out this value easily. Okay, and we got that is equal to sine square omega t over 2. Look at this. Initially we have taken the state as, or initial state was Sx plus. Okay, and at later time t, we are finding the probability of Sx plus is equal to cos square omega t over 2. Okay, but at later time the probability of finding Sx minus state is equal to sine square omega t over 2. That means at later time initial state was Sx plus state, but at later time there is a probability of finding Sx minus state too. That we have solved here, or we got a conclusion that initially we have taken, even though initially we have taken Sx plus state, at later time t we are getting a probability of finding Sx minus state at later time, Sx minus state at later time. That means this magnetic field, we are applying a magnetic field. That magnetic field is the cause of the rotation of the spin state into Sx plus. Initially it was Sx plus state. So magnetic field rotates this Sx plus state into Sx minus state at later time. Okay. And we know how to find an expectation value of an operator A, that is equal to sum of A dash expansion coefficient, sum of A dash into probability of finding the state into A dash into the eigenvalue. Okay, so by using this equation, let's find the expectation value. Let's find the expectation value of Sx. There is the probability of finding that particle in Sx plus state is cos square omega t over 2, and the eigenvalue is h cross over 2, and the probability of finding that particle in Sx minus state is sin square omega t over 2, and the eigenvalue is minus h cross over 2. That is equal to, if we are adding this one, we will get h cross over 2 cos omega t, because we are taking this h cross over 2 outside, and we will get cos square omega t over 2 minus sin square omega t over 2. That is in the form of cos square theta minus sin square theta. We will get cos 2 theta. So we got this answer, h cross omega t, h cross by 2, h cross over 2 cos omega t. Similarly, we will get, if we are finding the eigenvalue, if we are finding the expectation value of Sy, we will get h cross over 2 sin omega t. And if you are finding expectation value of Sz, that is equal to, we will get, that is equal to 0. That means we are getting a finite value for Sx, and we are getting a finite value for Sy, and we are getting the expectation value of Sz as 0. That means the spin precesses in the xy plane, not in the z plane. It's precesses in the xy plane. Okay.